Hello everyone. Here we'll discuss about the continuity equation in fluid mechanics. The continuity equation is basically another form of the mass conservation law, which says that mass can neither be created nor destroyed unless we are talking about nuclear reactions where mass can be converted into energy. But otherwise, the mass entering a certain control volume must be equal to the mass leaving that volume, and otherwise if they are not equal, the mass inside that considered volume will either increase or decrease based on the difference between the inflow and outflow rate. So that same thing can be written in this way, that is, in a control volume, the difference between rate of inflow and rate of outflow must be equal to the rate of change in mass in this volume, in the control volume. Now try to understand with an example, a simple example. Let us consider a container. This container is fitted with an outlet pipe through which water can leave this container, and we are filling this up with another pipe. So this pipe is filling up with at a rate of 2 liters per second, for example, and through this outlet, water is leaving this container at a rate of 1.7 liters per second. Now, if we want to talk in terms of mass instead of volume, then it would be 2 kgs per second, and this will be 1.7 kgs per second. Now, what is the difference between this inflow and outflow? It is 0.3 kg per second. So that means in this container, right now, suppose the total storage is about 10 liters, or maybe 20 liters maybe. So every second, if this is the rate of inflow and this is the rate of outflow, then every second the total storage in this container will increase by 0.3 liters or 0.3 kgs. So that's what is meant by this statement, that is in a control volume. In this case, the control volume is the total volume is of the container. That is total capacity of the container. So the difference between the rate of inflow and rate of outflow, that is this 2 liter per second or 2 kg per second and this 1.7 kg per second, must be equal to the rate of change in mass, that is this 0.3 kg per second in this control volume. So this can be written in equation form as I minus Q, where I is the inflow rate and Q is the outflow rate, should be equal to the rate of change of storage, that is ds by dt, where S is the storage and ds by dt will be rate of change of storage. Now here I may be mass per unit time or it can be volume per unit time, but since this continuity equation statement is written in form of mass, in terms of mass, so let's consider this is mass per unit time and this is again mass per unit time leaving, and this ds by dt is mass per unit time, that is which is increasing or decreasing inside the volume. Now if the density of the fluid while entering, while being stored and while leaving remains constant, that is only one density, in that case we can cancel out density from all these terms, and this becomes just volume rate of inflow, volume rate of outflow, and this is just the volume stored inside the control volume. Let's try another simplified example, which is a pipe of variable diameter. Suppose water or some kind of liquid is entering through this surface, this cross section, and leaving through this cross section. Here the cross sectional area is A1 and the velocity is V1. Here the area is A2 and velocity is V2. Therefore A1 V1 equal to A2 V2. This is a familiar equation that you may have used in your earlier classes. Now this A1 V1 is the inflow into this volume between this cross section and this cross section, and A2 V2 is the outflow, that is volume leaving through this cross section per unit time. So this is inflow equal to outflow now. Now let's look at this equation. It was inflow minus outflow is equal to the rate of change of storage. So what's the difference here? In this case, since the pipe is completely filled, unlike this container where it was not completely filled. So in this case, since the volume cannot change, the volume is remaining same. Therefore, and if the density is also remaining same, then the storage inside this control volume between this cross section and this cross section inside the pipe, it cannot change. Therefore, I minus Q is equal to 0, and therefore I is equal to Q. And that gives us A1 V1 equal to A2 V2. Now let's take another example. This is the example of a tire, a car tire suppose, which is being filled with air from some pipe, some pump. Now, the tire is a fairly rigid object unless you put a lot of pressure from outside. It doesn't change its shape and therefore doesn't change its volume. Now, while you're filling it up, that is, you're filling it up with an inflow rate, suppose I equal to some X kgs of air per second. So what is happening to the outflow? The outflow is 0, unless there is some puncture. We'll talk about that later. If there is no puncture in this tire, then inflow is this much and outflow is 0. So I minus Q should be equal to ds by dt, that is rate of change of storage inside this volume of the tire. Now, in this case, this S is the mass of air inside this tire. So the mass is given by rho into V, which is density into volume. Now volume is remaining constant here because the tire is having constant volume approximately. So what is changing in this case? The changing quantity in this case is rho, that is the density. So as you are filling this tire up using a pump, then the volume is remaining constant. Only thing is the density of air inside the pipe is increasing. Now if you consider a tire which is punctured, then you are filling it up with certain rate, suppose X kg per second, and air is leaving this tire through this small puncture hole at a rate, suppose Y kg per second. So the rate at which you are filling this tire up is X minus Y kg per second. Another very simple example of this one is a branched pipe. So a branched pipe like this, through this cross section water is entering at a rate of A1 V1, where A1 is area and V1 is velocity, and through this cross section water is leaving at a rate of A2 V2, and through this cross section it is leaving at a rate of A3 V3. So in this case, this is our control volume, and assuming that the density remains same and the pipe doesn't have any other puncture holes and so on. So in this case, A1 V1 is equal to the summation of the outflow through both these cross sections, A2 V2 plus A3 V3. So this way the continuity equation is useful in different situations. For these situations, we can fairly simplify the continuity equation based on our need. Now, let's try to find out the continuity equation in a very generalized form. So in this generalized form, whatever we write, for any specific situation, we can simply simplify this generalized equation by ignoring some of the terms maybe, and that way we can use or extract the form that is required for us from this overall generalized equation. So let's try to derive that generalized continuity equation based on Cartesian coordinate systems. So here we are going to consider a control volume which is having an elementary volume having the shape of a parallelepiped, and its dimensions are dx in x direction, dy in y direction, and dz in z direction. Therefore, the total volume of this element is dv equals dx dy dz. Now this is a small elementary volume in a flow field where fluid is flowing. So whatever is the velocity, it may be some inclined velocity in any of the directions. So that velocity will have components in all the directions x, y, and z. Suppose the x component of that velocity is u, the y component is v, and the z component is w. Now, let us consider this phase. Water or fluid may be entering this phase, it may be leaving this phase, and so that can happen to all of these surfaces. Now, when that happens, we can find out how much fluid flow is taking place through each of these surfaces. So, for a uniform sign convention, let us consider that when we are considering inflow, that is positive, that is when flow is taking place into the control volume, that is considered as positive, and when it is taking place, when it is leaving the control volume, then it is negative flow. Now, let's consider this surface. This surface has an area dy dz, and if this was the flow velocity, overall flow velocity, then its x component will be in this direction. So the net amount of fluid entering through this surface will be given by its area multiplied by the x component of velocity u. That is, the rate at which fluid is entering through this surface is given by velocity multiplied by the area. That gives us volume per unit time, and when we multiply it with the density rho, then it will give us mass entering per unit time. Now, if you consider this surface here, through this, suppose fluid is leaving at a rate. Now that rate will be given by velocity at this point, the velocity in x direction at this surface, and the area multiplied with the density at this point. I'm mentioning density at this point because we don't know whether the density will be remaining same here and here. Therefore, let's consider that density at this point is it may be different. If that is the case, then what we can write about the rate of mass flow through this surface? Let's say velocity is changing in the x direction. So the rate of change of velocity in x direction will be given by del u by del x. Similarly, if density is also changing in the x direction, it may change, it may not change, but let's consider for the sake of generality that it is changing. So the rate of change of density in the x direction is given by del rho by del x. So from this point to this point, the distance is dx. Therefore, the new density at this point will be rho plus the rate of change of density multiplied by the distance. Similarly, the velocity at this point, the x component of velocity at this point is given by u plus the rate of change of velocity del u by del x multiplied by dx. So this is the new density and this is the new velocity. Therefore, we can write that the amount of fluid leaving the control volume through this surface is given by rho plus del rho by del x into dx into u plus del u by del x into dx. So that is the new density multiplied by new velocity multiplied by the cross-sectional area, which is dy dz. Now if we expand this, then rho multiplied by u, then rho into del u by del x dx plus u into del rho by del x dx multiplied by rho u del rho by del x del u by del x into dx square. This term is very small because it's the multiplication of four very small terms. You see, del rho by del x is very small, del u by del x is very small, and dx square is again multiplication of two very small terms. So therefore we can obviously ignore this. Now the difference between this inflow and this outflow can be this original rate of inflow through this surface minus the rate of outflow through this surface, and the difference will be given by minus del x of rho u dx dy dz. Now the same thing can be found for y and z directions as well. So in y direction, the difference between inflow and outflow will be minus del y of rho into v, where v is the velocity in y direction, into dx dy dz, and in z direction it will be given as minus del z of rho w dx dy dz. Therefore, the total difference between inflow and outflow, when we consider all the components in x, y, and z direction, it will be the summation of these three terms. And since all of them have dx, dy, and dz common, so we can write it as minus del x of rho u plus del y of rho v plus del z of rho w. This whole thing is multiplied by dx dy dz. Now, according to the law of conservation of mass, this difference between inflow and outflow, the net difference between inflow and outflow, must be equal to the rate of change of mass inside the parallelepiped or inside the elementary control volume. Now, in this case, this rate of change of mass will be del T of the mass inside the control volume, that is rho into its volume dx dy dz. So that is del T of rho dx dy dz. Now these two terms must be equal, so we can write minus del x of rho u plus del y of rho v plus del z of rho w, whole thing multiplied by dx dy dz is equal to del T of rho dx dy dz. Now in this case, dx dy dz and dx dy dz on both sides can be cancelled, because these are not variables, these are just constant quantities, which is the dimension of the control volume. So it can be cancelled from both sides. So the simplified form of the continuity equation remains as del x of rho u plus del x y of rho v plus del z of rho w plus del rho by del t is equal to 0. So this is the general form of the continuity equation in 3 dimensions, and it's applicable to any type of flow. See here, the rho term is also under differentiation. That means this will be applicable for both compressible and incompressible flow. If the flow is incompressible, that is rho doesn't change, in that case del rho by del t will be 0, because rho doesn't change, therefore its rate of change will also be 0. In this case, we can simplify this whole equation to del rho by del x plus del v by del y plus del w by del z equal to 0. So this is the continuity equation for incompressible fluids, and this by default becomes the equation for steady flow as well. Now for 2 dimensions, we can write this equation. We can ignore any one of the dimensions. That's for this example, we can ignore the z direction. So the equation becomes del u by del x plus del v by del y equals 0. And if you only consider one dimension, then del u by del x is 0. So this is the continuity equation. We'll try to do some problems based on this equation in some later lecture. So that's all for this one. Thank you.